Okay, welcome back. We are working through factoring quadratics, and this one that we're looking at here. And let's get to writing down the quadratic that we're working on. I'm going to choose the color black, and Justin's with me, so Justin and I will be working through this together. I'll be guiding Justin through this. Okay. So Justin, you wanted to work on, sorry, it wants me to upload the drive, which I just did. Okay, so Justin, here's our quadratic number 2 here. Okay, so if we were to look at this, this is Sherman's class. So now, when we factor, or we're trying to find the zeros of a quadratic, we always want to put it into, oftentimes we want to put it into standard form, okay, and then set it equal to 0. Okay, in this case, we need to notice something about each term, okay, and so really what we're looking at here is ax squared here, and it's not set to 0, it's set to 1, okay?
Mm-hmm.
But what do you notice about the a term here?
It is even.
Okay. Okay, so before we move through there, let's see if we can rely on our, let me change colors here. Let's see if we can't rely on our factoring flowchart. Let's go back over here to the left and check our factoring flowchart, okay? So the first question is right here. Does it have 4 terms? Does it have 4 terms? No, so we wouldn't try to factor by grouping, okay? Then we're going to go over here, go over to this side. Is there a greatest common factor?
Well, there's only one term, so I guess there is.
Okay, so remember the greatest common factor in our previous problem was it was 2x squared minus 48x plus 90. That was it. And then we factored out the 2. So we wound up with 2x squared minus 24x plus 45. So in that situation, the 2 was the GCF. Okay.
So for this one, I guess it would be 4 then. Yeah.
Okay, but notice over here there's only one term. Okay.
Yeah.
So since there's only one term here, we're going to say it's a no. Okay, and that it's going to be a no. Okay, there's no GCF, and so we are going to go down this way. We're going to go to the right because there's no GCF. Okay, and then we are going to either go to this question or to this question. Okay, and so I want to go, and so they're teaching you a different method, really. But at this point in time, what I would do with this is I would put this, I would do some math here and set it equal to 0. So I would have to subtract 1 on both sides. So I'd subtract 1 on both sides of the equation. And over here, 1 minus 1 would be 0. And I would wind up with 4x squared minus 1 equals 0. So that's considered standard form. Okay, that's standard form right there. Okay, even though it only has 2 terms. Okay, and so if I were to compare the 4 and the 1, there's no GCF. Okay, so now I'm dealing with 4x squared minus 1. And so the question is, goes to this one next. Is it the difference of two perfect squares? So first of all, there's a minus sign, so that is a difference. Okay, when you're finding the difference of two numbers. Oh, okay, hang on a second. Miss C's in the waiting room, hang on. Okay, we're back, and we decided to put this equation into standard form. So now we have 4x minus 1 equals 0. And so it is in standard form. It does not have a b term. It has an ax squared term, and it has a c term. And so now, looking back where we are on our flow chart, we asked, is there a GCF? And we didn't have one. And then we came to the question, is it the difference of two perfect squares, or is it a factorable trinomial? And so we are looking at that. And so the question is it the difference of two terms? Yes, it is, because it has a minus sign. And is it the difference of two perfect squares? Is that a perfect square? And is that a perfect square? Well, we can look at the definition of what perfect squares are. A perfect square is when you take a number and you divide it, you take the square root of it, not divide, take the square root, and then you get a whole number. So let's take the square root of 4. Yep, you take the square root of 4 and you get a whole number. That's a perfect square. Let's take the square root of x squared. Well, the square root of x squared is going to give us x. So that is considered whole. That checks out. Let's take 1. What's the square root of 1? We don't take the square root of the minus sign. We just take the number itself. Well, square root of 1 is 1. So yes. So yes, we would say the answer to this question is yes, it is the difference of two perfect squares. So now we would come into this situation right here. Okay, so this is x squared minus y squared right here. Okay, so if I were to put that up here, x squared minus y squared, that's the pattern that we're looking at. And so what they're saying, let me go back and change my color, is that I'm going to have x plus y and x minus y. Okay, so notice I'm not using 4, I'm using x. Okay, so I took the square root of each one. So x in this case would be 2x. The square root of 4 and the square root of 4x squared. The square root of 4 is 2. The square root of x squared is x. And so if you wanted to do it all together, the square, hold on, got ahead of myself. So the square root of 4x squared, and let me extend my square root. My square root of 4x squared is 2x. Okay, so that's what I would put in here. And so the pattern is going to be x plus y, so the 2x plus, well, my square root of 1 was my y here, so that's 2x plus 1. And then the other side of it is 2x minus 1. That's how that would work out. Okay, so those are my factors, and then I would use the zero product property. 2x plus 1 equals 0, or 2x minus 1 equals 0. I have a handy dandy little writing pad here, but I haven't figured it out. It's a little more complicated, and I'll figure it out one of these days. Okay, so then, Justin, I would subtract 1 from both sides here. Okay, that would give me negative 1 over here. This would create 0, so I wind up with 2x equals negative 1. Divide out the 2 on both sides. And I wind up with x equals negative 1/2. Okay, so there's one of them solved right there. X equals negative 1/2. And then over here, I would add 1 to both sides. Let me choose a different color. I think I'll choose purple. Let me erase. It jumps out a little more. As you can see, the writing's getting close. You know, there's notes over here. Let's keep this out. And this was this work over here. Okay, now we'll do this work. I'm going to add 1 to both sides here. So I'm going to wind up with this. This adds up to 0, so we'll take it out. 2x equals 1. Divide 2 on both sides. These two create 1, which is just x. That's an x. X equals 1/2. So those are your two values. So that's how you can use that. But then if you look back into your, I'm going to stop sharing and I'm going to ask you to share at this point, Justin. Okay, so scroll up a little bit. So now they gave you A, solving using the square root method, B, solve in vertex form, C, solve by factoring, or D, solve by quadratic formula. Which one would you say that we just did?
I think we used A, solving using square root.
Right, we did. And that would not be wrong to say that we did it that way, okay? But then I'm going to show you a different way to solve this problem that might be a little quicker. But I just wanted to show you the how you would think through this. And that's really what they're trying to teach you if you were to use the factoring flow chart. But there's another way that you could do that. Okay, stop sharing, please. Okay, so let's jump back to where we were. And here's an alternative way. So this was factoring, and you would not be wrong to say that. But really the whole point of this is to critically think about how to solve these problems and do it in an efficient way. So if you look at how much work we did up here, that was a lot of work.
Yeah.
Oops, I'm sorry. That just was. Okay, we wound up going through, we did our checks, and we wound up here. Okay, and that's nothing wrong with that. But there's something in here that in this factoring flowchart that's just not represented by one of the strategies they're using, and that was solving by taking the square root. This is the square root method, and so and this was something that they taught. They taught it a little bit differently, and so I'll just go over that. And so what you need to just key in on are the perfect squares, okay, which we did through factoring. But even before we factor, is just looking at this and recognizing, hey, that's a perfect square, and hey, that's a perfect square. And so, bam, I'm just going to hit both sides and use the properties of equality and just take the square root. And so over here, I wind up with 2x, okay? And then over here, I would wind up with 1. However, I think you and I discussed this. You know, when we take a perfect square, what we're doing is, in this case, we took the square root of 1. Let me erase this.
I don't know if you were intending to share your screen because currently you are.
I can't see you. I'm sorry. Say that again.
You're currently not sharing your screen if you were intending to.
Oh, thank you. Yeah. Okay, hang on. Let me pause. Let me pause this. Okay. We are now sharing again. So I'm going to have to, you know what I'm going to do is I'm going to pause. I can join the conversation again. Okay, so now we're discussing, catching everybody up. We're discussing the nature of perfect squares. Okay, so, and how they could be positive or negative roots. So in the first situation, that's a positive 1. And so 1 times 1 were the roots, and it gave us a perfect square of 1. Well, what if the original number was not positive 1, but it was negative 1. Well, we'd wind up with negative times negative here, negative 1 times negative 1. Okay, and that's also a positive 1. So when we try to do the inverse and take the square root of a 1 and we arrive at a 1, we don't know if this 1 was positive or negative. So we always have to include both roots just in case.
Yeah.
Okay, so that is positive and negative 1. Okay, so that's how we come up with that plus minus thing. Okay, just a really quick review of that. I know you and I talked about that earlier. So now what I've got here is 2 dividing out over on this side. And then I have both positive 1 over 2. So positive 1 over 2. And I've got x equals negative 1 over 2. So that's the square root method. And so now it's good if we just kind of look at things and ask questions. Which was faster, the square root method or factoring?
I definitely think the square root method was a little quicker.
Absolutely. It absolutely was. Okay, so I'm going to pause this recording and then. Okay, we are back and we've worked through that problem off camera. I hope that was enough for whoever's watching this. Those of you who are still with us, thank you. We're going to move on to another kind of problem. And here it is right here, this quadratic, 3x squared minus 2x minus 7 equals 0.
Oh, wait. Yeah.
Hang on just a second. Okay, so we have the right problem. The first thing I want to note is that this is in standard form. We have the leading the leading term is being raised to the second power. And then reducing the exponent this is to the first power, even though there's no number there. And then a constant term, just negative 7 without a variable, and then set equal to 0. So it's in standard form. So we go up here to our factoring flowchart. We want to see if we can factor it. That's the reason why we check the factoring flowchart. The other thing, you wouldn't use factoring if you could solve it more efficiently by using the square root method. That would be the first thing. Right now, this is not none of these are perfect squares, so we wouldn't use the square root method. The first, and then the next thing is we would check: does it have four terms? Nope, it only has 1, 2, 3 terms. 0 is not considered a term because it's on the other side of the equal sign. So it's only this that we're looking at, and there are 3 terms there. So we would not do this. Okay, we would not factor by grouping. Okay, so now we're still trying to find out if we can factor this. And so now we want to check and answer the question. The next question is there a greatest common factor? And so I have a 3 here and I have a 2. Those do not have common factors. And so right away, we know that it's a no. It's a no. And so the next question is this one right here. Is it the difference of 2 perfect squares, or is it even a factorable trinomial? So we're going to try and see if it's the difference of 2 perfect squares. We really want to get that, okay? So this is a perfect square, but the 3 is not a perfect square. Okay, so all it took was, and remember, the difference of 2 perfect squares is when you have x minus y, just 2 terms being raised to the second power. That's not what's going on here. What we have here are 3 terms, and none of them are perfect squares. Okay, so no, it is not. So we can't go this way. So now we're brought over to this situation. Is it a factorable trinomial? And so we've been using a visual to see if it's factorable, and this is called Xbox, this little strategy. And so in the middle here is just the x term, the x variable. Up here we have a times c, and this is your a, so that'd be 3, and then this is your c, negative 7. So 3 times negative 7 would be negative 21, so we'll put that up there. Down in the bottom of the x box, you put your b term, which is negative 2. So down here is your negative 2. So what I'm looking for are numbers that will add up to be negative 2, but multiply to be negative 21. And so I'm going to look at the factors. I'm sorry, I miswrote. I meant to write 21 here. So I'm looking for factors of 21. And there are only 2 factors of 21, 3 times 7. And so what I need to do is I need to think of if I were to combine 3 and 7 in some way, is that ever going to equal negative 2? So if I did 3 minus 7, that would equal negative 4. Okay, and that is not equal to negative 2, so this would not work. Okay, I could do 3 plus 7. That equals 10. Okay, that's not negative 2, so this would not work. I could do it the other way around. I could do 7 minus 3. That equals positive 4, and that does not equal the negative 2 that I have. So far, it doesn't. I'm not finding any factors. Or I could do negative 7 plus 3, and that equals negative 4. That's not going to work. So let me see if I've used all of the strategies. I could do negative 3 plus 7. That equals 4. That does not work. I could do negative 3 plus negative 7. Just checking all the combinations. That equals negative 10. That does not equal negative 2. So none of the factors that make up 21 will give me the combination that I need. So the answer to this is it is not factorable. It is not a factorable trinomial. And since it's not a factorable trinomial, I cannot factor it. So I'm forced to use the quadratic formula. And I need to change my factoring flowchart, and I need to use the quadratic formula. Okay. When you take the next class or you get into pre-calculus, there's another way to do this. It's called completing the square, but this is integrated math 2. It's not one of the standards for this, but we're going to have to use the quadratic formula. Okay, and so I will stop recording and we will talk. I'll check right back with you. Okay, we're back, and we are going to use the quadratic formula. The first thing I need to do is realize that I'm in standard form, and so a is my first term. A is equal to 3. I'm going to list it right here. My a is 3. B is my second term. B is equal to negative 2. C is my last term. C is equal to negative 7. So I have my values here, and now I need to write out the quadratic formula. So here's the thing. Let's see if I can remember the quadratic formula here. It's been a long time, but let's see if I can. I believe it is x equals b squared minus the square root of x squared. No, that could be wrong. No, that's not going to be right. No, I'm gonna need you to help me.
Mr. Oxford,
I think
have it.
Is it 4ac there?
Here it is. It is x equals negative b plus or minus
Okay.
square root. So the b squared is on the inside of the square root.
Ah, thank you. So this is a negative b, and this is a plus or minus
Yep.
b squared minus 4ac.
Yep. You got it.
Okay, all over 2a.
Mm-hmm.
Okay, so here's the other thing. This part underneath here, That's called the discriminant. You can use that and to quickly find out if a quadratic is factorable, and that's another discussion. But we could have used that to figure this out. Okay, so now we're just going to substitute. My b is -2, so that's going to be negative, opposite of -2, plus or minus the square root. My b is -2 again, so that's squared, minus 4. My a is 3, so 4 times 3. And my c here is -7. And all of this is over 2 times a. So 2, and then my a is 3. So, and then I'm going to follow the order of operations on this. So x equals this. So the order of operations says to do parentheses first, and then any exponents, and then multiplication. Oops, that's an m. Let me make that a nicer m. Multiplication and division, addition and subtraction. So parentheses, I'm checking for parentheses. And so this big giant square root here, this is really treated as a parentheses. So inside the parentheses, I have exponents, I have subtraction, and I have multiplication and multiplication. So inside the square root, I am going to do exponents first. So that means -2 squared, that's 4. Okay, I'm going to keep this square root up here. And then I've got -4 times 3, that's -12. I'm going to put -12 up here. And then I have the -7, so I'm going to have -12 times -7, and that's going to be a positive number. And I believe it's 96. So I'm going to wind up with positive 96 here. Okay, and I'm going to keep working underneath the square root. So now what I have left under the square root is addition, because remember, I'm still working on PEMDAS here. I'm still in parentheses. So that equals the square root of 100. Okay. And so now I've got all that written out, but now I'm just going to see if I can do this. I'm going to go back here, and I'm going to erase all these steps just because I'm going to run out of room. It's all these notes that I did. And really what I've got here, after doing all these steps, is, whoops, I erased too much there. I am going to write in the square root of 100. So let me put the division bar back in. And so now up here, I've just got the square root of 100. All that math I did, all those order of operations, calculated out to square root of 100. So what do we know about 100? What do we know about 100? Well, we know that it's a perfect square. We know that the square root of 100 is 10. 10 times 10 equals 100. So therefore, the square root of 100 is 10. So I'm just going to write 10 in here. I'm simplifying. I wouldn't do this with paper, but since we've got so far to go here. Okay, so now I've done all my parentheses. Okay, I've done parentheses. Now I'm checking for exponents. Are there any exponents here? Nope, there are no exponents. Okay, is there any multiplication? Yes, there's a -1 here. I'm talking about right here, negative times -2. Well, that's just negative times a negative is positive 2. So I'm going to clean that up. And that's going to be positive 2. And then I can also do multiplication down here. I've got 2 times 3. Well, that's just 6. So I'm going to simplify this a little bit more. And that's 6 down here. So I've done all the multiplication that I can do. And then I'm going to clean up this division bar a little bit. So now what I've got is 2 plus or minus 10 divided by 6. And what I notice is that 2, 10, and 6 are all divisible by 2. So I am going to simplify and use division here. So 2 divided by 2 is 1. 10 divided by 2 is 5. And 6 divided by 2 is 3. And so I think at this point I can rewrite this equation as x equals 1 plus or minus 5 divided by 3. And so at this point I've got everything in lowest terms. So I would go 2 different directions with this. I would wind up with x equals, and now I've got 1 over 3 here. I would treat this as 1 over 3 plus, see, I'm going to just use plus here, plus 5 over 3. Okay, so I wind up with just addition over here. And then I could go the other way and show the other. The positive root I did over here. There's plus. And then over here I'm going to wind up with x equals, oops, my equal sign's a little unclear. Let me rewrite that. So over here I wind up with x, and then this 3 can go underneath this 1, so I'm going to have 1/3, and I'm going to use the negative root over here. So this would be minus, and then it'd be minus 5 over 3. That's how that works. Okay. That's 5/3. It's really hard to read. See if I can move this a little bit. Give ourselves a little more space. Yeah, it looks like I'm going to have to erase a little bit. This is my work from a previous problem down here. We'll erase this. This work down here doesn't have anything to do with this problem. So just try to be clear and not so confusing. A little less visual stimuli. Yeah, I could erase all day down here. This is going to take too long. So anyway, just maybe I'll just draw a line. This doesn't have anything to do with what we're doing. Okay, so now I have 1/3 plus 5/3. That is going to be 1 plus 5 over 3, which is equal to 6/3, which is equal to 2. So I have x equals 2. Okay, that's one of my roots. It's one of my solutions. And then over here I'm going to have x equals 1 minus 5 over 3, which is equal to negative 4 over 3. And I like to leave it as an improper fraction, but some people like to change it to a mixed fraction. That would be the same as negative 1 1/3. You could do that. Or you could just say this is it, but either one's okay. Okay, so that's that. I'm going to stop sharing and then we'll talk. Okay, thanks.